How's it going, everyone? We're going to be talking about a car driving on a banked curve. So, this is the situation where the turn on a road is not horizontal. Okay, this mass here represents our car, and you can imagine this is actually a curve where the car is moving this way. If we were to look from the top, we actually have the car right here, and it's moving along a curve. And this doesn't have to be a circular road, because the road could be making a turn like this, right? So the car is on a circular path for a certain period of time. Now, in that situation, the net force acting on an object moving in a circle like this is the centripetal force, okay? And that is equal to the mass of the object times the velocity squared divided by the radius. Now, why is there this centripetal force acting or pointing in the center of the circle? Well, remember, force is proportional to the rate of change of velocity, right? Because force is your mass multiplied by your acceleration. Right? Your acceleration is your rate of change of velocity with respect to time. Okay, so at this point, your velocity is here, and at a later point, your velocity is here, right? At a later point, your velocity is here. It's always tangential to the circular curve. So in what direction is your velocity changing? Right? What's the rate of change of your velocity? Well, if we take this vector here and place it like this, well, it's actually changing towards the center of the circle. Take this vector here, place it there, right? The change is actually towards the center of the circle. That's why centripetal force is pointing towards the center of the circular path. So we're going to talk about what that centripetal force is equal to and what the maximum velocity is that the car can move at. Because if it moves too fast, well, it spins out, right? Or in this case, it spins out. And the purpose of this curve, or this incline, this bank in the road, is to make it more difficult for the car to spin out, because it would have to work against gravity to spin out. If you don't have that incline, well, then your centripetal force is just the force of friction, which keeps your car from spinning out. But with that incline, things get a little more complicated. Here is our banked curve right here that we're looking at from the side, all right? And there's our vehicle here, right? It's moving on this kind of circular path. And in this situation, there's only two forces acting on the car, right? There's the force of gravity, which pulls it down, right? That's equal to the mass multiplied by gravitational acceleration. And there's the normal force, which is at a 90-degree angle from the surface that the car is on. And that's it. Those are the only two forces acting on the vehicle. And so they have to add up to the centripetal force, which is horizontal. Okay? Now, when we first start talking about a mass on an inclined surface, we see that, well, if we add the normal force and the gravitational force, the result is actually down the slope, right? So where does this extra bit of normal force come from, which results in the net force being horizontal rather than down the slope? Well, the normal force is just the surface reacting to a mass pushing into it, right? So you have, say, gravity pushing down, and the normal force is the surface trying to take back its original form. Well, if your car is moving around in a circle right here, right, Well, this car moving that way, it's actually moving into the road, right? It's moving forward, but the road is curving, blocking the path from moving forward. Your car is actually moving into the road. So the surface is being pushed into, right, or instead of forward, because that kind of looks like up, is being pushed into, not just from gravity pulling the car down, but from the car itself moving forward, pushing into that surface, right? And that will create even more of a reaction force, being the normal force, and so you have a stronger normal force, and that's why the net force of adding the normal force and the gravitational force, because of that extra bit of normal force, your net force ends up, or your total force ends up being horizontal. Okay, now let's also talk a little bit about geometry. All right, so this angle of inclination, let's call it theta. All right, and because this is 90 degrees, this must be 90 minus theta. And that's because the angles of a triangle have to add up to 180. That's how we know that this is 90 minus theta. Well, let's draw our vertical component of the normal force. All right, so we've actually got a Z pattern here, which means this angle here is also 90 minus theta, right? There's our Z pattern, okay? And so if this is 90 degrees right here, and this is 90 minus theta, well then the rest of that 90 degree angle must be equal to theta. Okay, so the angle between the vertical component of normal force and the normal force itself is also 90, and we're going to use that to make the following calculations. So I'm going to draw this incline again. Okay, there's our mass, there's our angle theta, okay, there's our force of gravity, Fg, there's our normal force, Fn, and they add up to the centripetal force, which is our total force here, Ft. Now, this normal force has a horizontal component and a vertical component. And the vertical component, which is this right here, okay, well, that must be equal to the force of gravity because the car isn't moving up or down, okay? The vertical forces acting on it balance out. Therefore, the vertical component of the normal force must equal the force of gravity, all right? But we also know that if we take the cosine of theta, okay, well, we get the force of gravity, right, that magnitude, right, because this length here has to equal to mg, right, divided by Fn. And we can rearrange that to say that Fn equals Fg divided by the cosine of theta. Okay, and we are going to use that later on. Now, what if we take the sine of theta? Well, the sine of theta is equal to Ft over Fn. Okay, and we can rearrange that to solve for Ft, right? Ft is equal to Fn sine theta. And combining these two formulas, if instead of Fn we put in Fg over cos theta, we get that Ft equals Fg over the cosine of theta times the sine of theta. All right, well, Fg is mass times gravitational acceleration, And sine theta over cos theta is the tangent of theta. So we actually get mg tan theta. And that total force is our centripetal force. So we have mv squared over r equals mg tan theta. And we can rearrange this to solve for our velocity. Okay, so v squared, our m's cancel out, by the way. Okay. So we just have v squared equals rg tan theta, and if we take the square root, we get that our maximum velocity is the square root of rg times the tangent of theta. Okay? So, first thing we notice is that the higher r is, the higher our maximum velocity is. Well, that makes sense, right? Because a larger r means you have a larger radius, right? So it's not as sharp of a turn, right? So your maximum velocity can be higher. A smaller r means you have a smaller radius, which means you have a sharper turn, so your velocity cannot be as high. We also see that a larger g, a larger gravitational acceleration, means that you can have a higher maximum velocity. Well, that makes sense too, because it's the gravitational acceleration that's the whole point of this this banked curve, right? It's harder to spin out because spinning out would mean moving upwards, which would mean moving against the force of gravity. And then we have that tan theta there. And this becomes pretty clear when we put in some extreme values. Okay, let's say theta is equal to 0. Well, that means that there is no inclined surface. You're just on a horizontal road. Well, the tangent of theta, if theta is equal to 0, right, the tangent is also 0, which means your maximum velocity is 0, okay, which means you're going to spin out. There's no incline preventing you from spinning out. And that's true, okay? If you have a horizontal curve, the only thing that's going to stop you from spinning out is friction. And in this analysis, we're not considering friction. So that makes sense. Now, what if we have theta equals 90 degrees? Well, if the incline of your curve is 90 degrees, then you just have a wall, okay? And your car is just driving along that wall, okay? This vertical surface. And in that situation, I mean, you can drive as fast as you want. As long as that wall doesn't break, you're not going to move through it, okay? And what do we have? Well, the tangent of 90 degrees is undefined, okay? So your maximum velocity is technically infinite, right? You could go as fast as you want along that vertical curved surface, provided that you're not falling down, right? You can go ahead and do that. So that makes sense there. So hopefully that makes this concept clear to everyone. I hope you enjoyed that. Until next time.